Imagine an AI agent that doesn't just solve problems for you, but actively rewrites itself to solve them better next time. It notices when it fails, generates its own training data, edits its own prompts, invents new tools when the existing ones fall short, and occasionally even patches its own source code. This is the promise of self-improving agents, and it's the subject of a sweeping survey from a team at KAUST, Jilin University, and IDSIA, led in spirit by Jürgen Schmidhuber, who has been thinking about self-referential learning systems since the late 1980s. The motivation here is both practical and philosophical. On the practical side, modern agents built on top of large language models are increasingly deployed in messy, open-ended environments like software engineering, web navigation, scientific discovery, and robotics. Static agents, no matter how clever their initial design, tend to hit ceilings. They repeat the same mistakes, fail to adapt to new tools or interfaces, and require constant human tuning. On the philosophical side, self-improvement touches the oldest dream in AI. Going back to J. Good's 1966 speculation about an intelligence explosion, and Schmidhuber's 1987 self-referential learning framework, and the theoretical Gödel machine from 2003, which would rewrite its own code whenever it could mathematically prove the rewrite would improve expected utility. What's changed recently is that foundation models give us, for the first time, a rich semantic medium, natural language, in which self-modifications can be proposed, evaluated, and applied without having to search through raw assembly code or synaptic weights. The survey's central move is to give us a clean formalism for thinking about what a modern agent actually is. Think of an agent as having two parts. The first is the foundation model itself, with its parameters. Call this theta. The second is the scaffolding around the model, which the authors call sigma. The scaffolding is everything that turns a stateless language model into an actor in the world. The prompts and system instructions, the memory system that remembers past interactions, the tools the agent can call, and the control logic that decides what to do when. Here's a useful analogy. If the foundation model is like a brilliant but amnesiac consultant who can only respond to whatever's put in front of them, the scaffolding is the office, the filing cabinets, the phone system, and the standard operating procedures that turn that consultant into a functioning business. Self-improvement, then, is any process where the agent uses signals from its own execution to durably modify either its brain, the parameters, or its office, the scaffolding. This gives rise to the survey's two-pathway taxonomy. The first pathway is foundation model improvement, where you actually update the weights of the underlying model. This is slower, more expensive, and harder to reverse, but the improvements are consolidated deeply into the model's capabilities and generalize across tasks. Within this pathway, the survey identifies three sources of learning signal. The agent might generate its own training demonstrations, essentially teaching itself by producing instruction-response pairs and then fine-tuning on them. This is the lineage of self-instruct and evil instruct, where you bootstrap a small seed of examples into a large synthetic corpus, sometimes with curriculum-style difficulty progression. Alternatively, the agent might produce evaluative feedback, scores, preferences, critiques, that it uses to align its own outputs, as in constitutional AI or self-rewarding methods. Or third, the agent might learn from actual exploratory experience in an environment, either a grounded one like a real code repository or web browser, or a simulated proxy world. The second pathway is scaffolding improvement, where the model weights stay frozen but the surrounding structure evolves. This is typically faster, cheaper, more reversible, and more transparent because the changes are stored as human-readable prompts, memory entries, or tool definitions rather than absorbed into billions of opaque weights. The survey breaks this pathway down by which scaffold component is being edited. Prompt optimization includes techniques that use scalar rewards to hill climb over prompt variance, qualitative critiques to iteratively refine prompts, population-based evolutionary search over prompt candidates like prompt breeder, and even textual gradients, where a language model computes something like a natural language analog of a gradient, explaining how a prompt should change. Memory evolution covers how agents decide what to write down, how to structure those notes, flat lists, hierarchies, graphs, or vector embeddings, and how to consolidate, retrieve, and forget over time. Tool governance covers dynamic routing among existing tools, iterative refinement of tool implementations, and full autonomous tool creation, where the agent writes new tools when the ones it has aren't enough. And finally, full scaffolding updates like the Darwin-Gödel machine, Alpha Evolve, and ADAS treat the entire agent architecture as the object of search, essentially rewriting the agent from top to bottom. One of the more elegant conceptual contributions is the notion of a skill as a reusable instance of the self-improvement operator. Think of a skill as a serialized update that can live in any of the substrates: a new tool, a workflow written into memory, a consolidated set of weights, or a control routine. This gives us a unified way to talk about how agents accumulate capability over time, regardless of where in the architecture the capability is stored. The authors further distinguish object-level skills, which act on the world like a learned routine for collecting wood in Minecraft, from meta-level skills, which act on the agent's own configuration, writing a new tool, refactoring a prompt, or patching one's own scaffold. Meta-level skills are the interesting ones for self-improvement, because when the skill that improves the agent is itself improvable, you get the self-referential loop that Schmidhuber has been chasing for decades. The survey does a careful job connecting all of this to classical learning paradigms. Parameter updates driven by interaction trajectories map cleanly onto reinforcement learning. The foundation model is just a large policy network being optimized with something like PPO or DPO. But scaffolding updates lie outside classical RL entirely, because they change the state and action spaces themselves. And because the objects being optimized, prompts, memory entries, routing rules, are discrete, structured, and typically edited through search or generation rather than gradient descent. The survey also draws connections to online learning, where forgetting and distribution shift are perennial concerns, and to active learning and artificial curiosity, where the agent chooses what to learn about. On applications and evaluation, the survey walks through software engineering agents that iterate on code with test feedback, web navigation agents that learn from browsing experience, gaming agents that self-play, scientific discovery agents, embodied robots, and general computer use agents. It also surveys the benchmarks used to measure improvement, distinguishing mechanism, benchmarks that isolate a specific self-improvement capability from domain benchmarks that measure end-to-end task success. A critical observation the authors make is that many evaluations conflate the two, making it hard to tell whether an agent is genuinely improving or whether its scaffolding just happened to be well-suited to a particular test set. The limitations the survey surfaces are worth taking seriously. Self-consistency filtering, a common trick for selecting good synthetic training data, fails when the model is confidently wrong because repeated sampling just converges to the same wrong answer. Curriculum decomposition can break when the subproblems don't preserve the constraints of the original task. Self-critique loops depend on the model being able to see its own errors. And if certain error types are outside the model's perceptual range, iterative refinement can actually amplify them rather than fix them. Memory systems face poisoning risks, tool interfaces can drift semantically, and full scaffolding evolution risks catastrophic regressions that are hard to detect. The authors are honest that we don't yet have good ways to guarantee that a self-improving agent will actually improve monotonically rather than degenerate. Now let's walk through some questions you might have after hearing all of this. First, why does the survey draw such a sharp line between foundation model improvement and scaffolding improvement, when in practice deployed systems mix both? The answer is that they're operating on fundamentally different substrates with different trade-offs. Weight updates are slow, expensive, hard to reverse, and produce opaque changes that generalize broadly, while scaffolding updates are fast, cheap, transparent, and easily rolled back, but tend to be more task-specific. Separating them cleanly gives us a common language to compare methods, even though a mature production system will absolutely combine both, perhaps using scaffolding edits for rapid adaptation and periodic weight updates to consolidate the most reliable improvements into the base model. Second, what actually is a textual gradient, and why is it interesting? A textual gradient is a natural language description of how a prompt or output should change to improve some downstream metric, produced by a language model that's been asked to critique a system's behavior. The reason it's interesting is that it lets you do something analogous to backpropagation through a pipeline of language model calls, where instead of numerical partial derivatives, you have a chain of natural language critiques flowing backward through the system. This is useful when the thing you want to optimize is discrete and symbolic, like a prompt, because you can't directly take gradients of it, but you can ask a model to tell you in words how it should change. Third, if the Gödel machine from 2003 was already the theoretically optimal self-improving system, why haven't we just built one? Because the Gödel machine requires the ability to formally prove that a proposed self-modification will improve expected cumulative reward, which is uncomputable in general and impractical even in restricted settings. Modern agents relax this by trading provable optimality for empirical improvement. They propose modifications, test them, and keep the ones that appear to help based on benchmarks or verifier feedback. The trade-off is that we lose formal guarantees and take on real risks of the agent gradually degrading or optimizing for the wrong thing, but we gain something that actually runs on today's hardware. For large-scale recommendation systems serving hundreds of millions of users, the ideas in this survey point to some concrete opportunities. The scaffolding versus parameter distinction maps naturally onto the split between fast, reversible changes to retrieval rules, ranking heuristics, and prompt templates for LLM-based re-rankers versus slower, more expensive updates, to the underlying embedding models or two-tower retrievers. A production system could adopt the scaffolding improvement pattern to let agents autonomously refine feature engineering pipelines, generate new candidate retrieval strategies, or evolve prompts for LLM-based re-rankers based on online A/B test outcomes, all without touching the core model weights. This gives you a rapid experimentation loop with easy rollback, which is critical when a bad change could tank engagement for millions of users. More specifically, the memory evolution literature has direct relevance to user modeling, where the question of what to remember, how to structure it, and when to consolidate or forget is exactly the challenge of building rich, evolving user representations from long interaction histories. And the tool creation paradigm suggests a future where recommendation agents can autonomously write new candidate generators or feature extractors when they detect coverage gaps, essentially treating the recommendation stack itself as a modifiable substrate that grows in response to observed user needs rather than being hand-engineered in advance.